couple of examples of surface flows, and I'll just go over it again. So we developed this kind of model where you have this layer which is flowing on a heap of the same material, and in the layer you essentially have a shear flow, and this layer is quite thin compared to the length of the layer. So we can assume that the flow is nearly unidirectional. We don't have to worry about the curvature and so forth. And so we can have a coordinate system where y is always perpendicular to the interface and x is always along the interface. And then we took a sort of macroscopic balance approach in which we are averaging in the y direction and also in the z direction. So we have all these equations. Over here, of course, I am writing the equations for the wall friction, coefficient of wall friction mu w equal to 0. So in addition to so this is the mass balance equation, this is the x momentum balance equation. And in addition to that, we need what is the shear stress in the flowing layer. So this is like a Bagnol term where stress is proportional to the velocity gradient squared, and this is a frictional term. This is the normal stress or the pressure multiplied by the coefficient of friction. So tan beta s or mu s is the coefficient of friction here. Whereas if you look inside the bed, then you have just pressure times the coefficient of friction. So these are the two stresses. And then if you combine all of these and simplify and so forth, assuming that you have a linear velocity field, constant bulk density, then you'll get these set of equations where this gamma dot is nothing but the shear rate. And so you have this u is just gamma dot into delta by 2. And then these are the equations which will tell you how the heap shape will change with time. This is the rate of deposition and so forth. And so you have 6 unknowns and there are 6 equations. So we can easily solve this. So we looked at one problem was on heap flow. So we assumed a pseudo steady state. And so the governing equations become simpler. And the source term becomes a lot like the BRDG model as we saw. And then if you look at the open heap flow, you have a continuous flow of material coming in, then it flows over the heap and then out. And so you have a constant angle, and that angle should be equal to beta m as per our theory, because if you see this, in this particular term, since it's at steady state, there's no material depositing and no material being eroded. So in this, gamma is equal to 0. So if gamma is 0, then beta must be equal to beta n. And it's a constant. And then also you'll have u times delta is a constant and u squared delta is also constant, both from the mass continuity equation and the momentum balance equation. So this gives us that u is constant and delta is constant. So you get u is just gamma dot into delta by 2. So this gives us the layer thickness. And then if we do the experiment, so this is like, this is actually a photograph. You can see these particles here. And you're pouring here at a constant rate, and then they flow down. And these are the fitted lines to this surface. So from this, we can easily get the thickness of the layer as well as the angle. And the way that we have looked at the free surface is easy to get. But if you look at this image, then you can see that here it's all blurred. That's because the particles are moving, and here the particles can be seen clearly because they're stationary. So we just arbitrarily decide on some interface between these two regions and then draw this so you can get the layer thickness and so forth. And then if you look at the measurements for many different cases, then you can see that this beta m actually increases with mass flow rate. This is because of the wall friction, and this line is a prediction of what you would get from the increase in beta due to wall friction. And then here you can see delta is increasing with mass flow rate. So this is also in agreement with the theory. So this goes as delta is mass flow rate raised to the power of half. So this is a mistake here. And that line is in fact the theoretical prediction. So, this whatever theory I've taught you, it matches the experiments reasonably well. Then the second problem that we looked at was, supposing you have a closed heap, that is, this wall is closed. So as you are pouring, the material flows down this surface and the heap will rise with time. And here what we say is that the rate of deposition at every point is the same, because you'll have a constant. I mean, the shape will be constant, it will not change with time. Only thing, it will just move up. So this gamma, which is the rate of deposition at each point, is uniform and constant. Because if the deposition is higher here, then the angle will start increasing. That is not something that we see. At steady state, you have a nice steady shape here, and it goes up at a constant velocity. So if we assume this, then we saw that delta is just going as this raised to the power of half, and then the source term can be given by this, where gamma we can easily relate to the mass flow rate. We saw this in the class. And here is some experiments. You can see this material coming here and flowing, and then this is the layer. So you have a flowing layer, this is a static bed, and then you can, by image analysis, you can trace out the shape of the layer. And of course, you can measure the height as a function of time. And one of the things you definitely see is that there's a nice straight line. That means another evidence that gamma is constant. And here is a comparison of the theory to the experimental data. This is for the layer thickness, and this is for the angle. And again, you get very nice agreement. And then, of course, you can see for the shear rate what is the prediction as opposed to the experimental measurement. So again, this shows that the theory is quite okay. The next one we looked at was the rotating cylinder flow. And here are some images of the flow in a rotating cylinder at different values of the Froude number. If you remember, Froude number is nothing but rotational speed squared into the radius divided by acceleration due to gravity. So, as this thing is rotated, you can see that you have a layer that is flowing. So again, you can see the fuzzy, because the particles are moving. So, you have, this part is fuzzy, but here where the particles are slowly moving and rotating as a fixed bed, you get, you can see the particles. So you can clearly make out the difference between the flowing layer and the rotating fixed bed. And what is interesting is that you see this layer here, but then as you go on increasing the Froude number, this layer becomes more vertical, the angle increases, and then, there's a shape also changes. And of course, this is keeping everything fixed and only increasing the rotational speed. And so what is actually happening is that the inertial terms are increasing. And so as a result, the particles are being pulled up. You will also have some centrifugal force, which is pushing the particles out. So you get this kind of behavior. And, these are just the shape of the layer. And here there are different Froude numbers. This is different particle diameters, and you can see that the shape changes. And then here again you have Froude numbers, but now here the cylinder radius is changed. And again you can see that the shape is changing as your cylinder radius is changed. So both Froude number, cylinder radius and particle diameter, everything affects the shape. But one of the things that is known is that if you plot the scaled profiles, that is if you plotted equal Froude number and you take different sizes, but if you take this size ratio, the diameter of the particle divided by the radius, if you take that to be the same, so if S is constant and Froude number is constant, these are the two dimensionless parameters, then you see all the profiles. So you can see different black dots and white dots and so forth here. This is for different equal Froude number, equal size ratio, but different size of cylinder, different size of particle. And you can see they match perfectly. So there's really nice scaling. And this is for some steel balls, this is for sand, this is for steel and for glass. So, you know, it's like two different materials which are very hard, but, you know, all the dimensionless parameters S and FR are the same. So even for two different materials, the profile shapes are identical. So this is known as scaling because you make everything dimensionless and then the flow looks exactly the same. Okay. So, you know, all of this stuff that I'm showing you is all done by one of the students in our lab, Ashish Orpe. Now, of course, he's a senior scientist at National Chemical Laboratory in Pune. So this work was done in something around 2000, about 20 years ago, in the year 2000. It's all published. Now, if you look at how to analyze these rotating cylinder flows, you remember this, right? That we can calculate gamma for the rotating cylinder flow simply from the rotational speed. And so this gives us the continuity equation and then the momentum balance equation for the flowing layer. This is the flowing layer in the rotating cylinder flow. So when you're looking at just what is going on inside this layer, then what it says is that the mass flux or the volumetric flux U times delta, how it changes with distance is given by this, and the momentum balance in there is given by this. And then if you solve this, then you can get, we saw in the limit where acceleration is equal to 0, or acceleration, if we put du by dx is almost equal to 0, then you know, we get this, we got a quadratic equation, and then when we solved it, we got u by delta is just given by this. And this u by delta you can think of as the shear rate by 2. We already know from this u times delta is given by this and u divided by delta is this. So if you combine these two, then you can get the layer thickness profile, which is just given by this. And then we made everything dimensionless, and then we saw that, you know, if we take the Froude number very small, then the profile becomes like this. But in any case, even for any arbitrary Froude number, if x is equal to 0, x equal to 0 essentially corresponds to, so, you know, if we have this as our profile, we put our coordinate system like this, y and x. So x equal to 0 corresponds to the place where the layer thickness is maximum. And that is, you know, over here you have delta at 0. So, you know, x equal to 0 just gives us that delta 0 is just this prefactor CS FR divided by A. So now we have got so much experimental data, now we can check is any of this thing correct? And here you can see, so first is of course the layer thickness at the middle, delta 0, for different materials, plotted versus S into FR divided by A. So that unknown parameter C is kept as a constant. And you can see this versus this gives you a straight line. Again, that is in agreement with theory for different materials. And from each you can get the value of this parameter C, which is related to the collisional resistance to the flow. And you can see that for the different materials, you get slightly different values. And here are the comparison of the profile with distance. So you see that when this is for different Froude numbers and for different size ratios and for two different materials. And you can see that if you don't make that this is the approximate solution corresponds to du by dx equal to 0. The full solution is that whole equation and we solve that numerically. So if you could do the full solution, it agrees extremely well. But for relatively lower Froude numbers, you get the approximate solution also works quite well. So the lines are the theoretical predictions and the points are measurements. And Ashish looked at all different Froude numbers from 0.002 to 0.064 and size ratios also by a factor of 10, and the model works everywhere quite well. So this is quite a robust model and it is very nice to see. I just wanted to show you that we had assumed that there was a linear profile. So you can actually measure what is the velocity profile over there by just looking at how the particles move. So if you take a photograph of this region, then it will look something like this. And we keep the shutter open for some time, delta t. So in that much time, the particle moves and it produces a streak like this. So this is just a magnified version of this region. You can see these three streaks. And then through image analysis, we actually fit some shape to these streaks. And from that, we can accurately calculate the length and the width and so forth. And then from there, we can calculate what is the velocity. And then, once you have the velocity, then you can easily calculate the profile by calculating the velocity in every bin and averaging it. So we can get all of these things, including the shear stress and everything. And then, Ashish, he actually did some very nice calibration by sticking some particles to the rotating cylinder surface and then just generating the streaks artificially, and he could get very, very good, accuracy for the method. And then these are just some of his results where this is the profiles that you're getting in the flowing layer. So this is the flowing layer, the particles are moving like this. And then this is the free surface, and then as you go down, the velocity decreases, and then finally get into the bed. And what we had to assume that it's a linear profile, so you can see it is in fact approximately linear. And then, again, as we have done all the scaling before, this also scales very nicely. When you take the particle diameter and the characteristic velocity, so if you put y divided by d, where y is this distance, and if you take x and you do, this is the velocity, if you divide that by square root of gravity times the diameter, then you get all the profiles collapse to each other. So here you can see that the profile you can say is almost linear, but one of the things is that we make an approximation because it doesn't just become, it's not like this. This is our model that we assume that it's 0 over here and it is a straight line over here. This is our model. But the actual, when you actually look at the profile, then there is a small, it's a sort of smooth decay. And then over here also there is a deviation. This is near the free surface because the particles are all flying. They collide with, and then they can jump. So that's why near the free surface also there's some deviation. And at the interface, there's not a sharp interface, but there's a slow. So, but to a large extent, at least in a macroscopic sense, as we are looking at, the theory works very well. And so those equations you can use whenever you want to do any analysis. And those, you may have one or two parameters to estimate, but the theory basically works. Okay. So this concludes what I wanted to say about rotating cylinders and so forth, and surface flows on heaps and things. And the next thing, what I'd like to do is now to move on to on a new topic, which also has some new ideas to think of. So here, this was what we did last time, this on the rotating cylinder and so forth. But I want to now move on to so today is 21/10/21. Nice. And we are on lecture 33. And what I'd like to talk about now is mixing. So mixing or blending is a very common industry application. And it's very important in many cases. Okay. So whether you look at, let's say, cement, you think of cement as a powder or something like this, but actually it's a mixture of many different components in there, which give it its unique properties. So it's not cement is not a single chemical entity. It has many things in it. And they have to be mixed together. So, cement will have gypsum, it will have some amount of calcium silicates, it will have various other things, and they all mix together. So cement is a mixture. And of course, during its formation, it gets blended. Then if you look at pharmaceuticals, but particularly tablets, so you have a very small amount of the active ingredient mixed into an inert powder. So one is cement, pharmaceutical tablets. So we have tablets, but if you see, the weight of the tablet will be a few grams. But if you see on the box of the medicine that you're having, it will say something like 5 milligrams, 10 milligrams, or whatever. So essentially the amounts that are in the tablet of this, whether it's a crocin or whatever, maybe 100 milligrams at the most. And the weight maybe of the tablet maybe 10 times more than that. So you have a very small amount of the active component which has to be mixed into that inert powder, and it has to be uniformly mixed. So, tablet to tablet, you cannot have variations. And like this, there are many, many other examples that you can think of. So mixing is a very important uh, operation related to powders. Just like you have for liquids also, mixing is very important. Here also there are many, many examples where dry powders are mixed. Another example could be in polymers. Very often you will mix more than one polymer together. So you have to mix the tablets first, mix the pellets first, and then very often they'll put many additives in there, which may be also powders. So all these things have to be mixed together, and then usually the whole thing is melted and then further mixed. So this initial dry mixing is also quite important. So there are many, many examples of mixing, and so that's quite an important factor, an important operation that we need to consider. And so the first thing that we'd like to do is evaluation of mixed state. So how do we know that the mixing is complete? So we have to do some evaluation and then try and figure out. So usually what the way it is done is, let's say for example you have some system, and then you are trying to mix different components in. So let's say white is something and black is something, and they're initially all separate. So this is I don't want it to look like some. Let's say you're trying to mix some amount of the black material into the white material through agitating the powder, rotating the container, whatever. Usually drum mixers are very commonly used, but there are many other kinds of mixers. I'll show you some examples later. So one of the key things is that how do you evaluate the mix state? And the way that it is done is to take samples, small samples from the various points in the system. So you just take samples. Let's say you take n samples. Then in this case, the mean concentration, or it could be just volume fraction or weight fraction or whatever, or number fraction, x bar is just xi, I going from 1 to n divided by n. So you have taken n samples, and each sample has a concentration xi. So if you take the mean value, then it will give you the mean value of the concentration. So xi could be anything. So it could be either volume, fraction of the species being mixed. Let's say black, or number fraction of the species, and so forth. So depending on whatever you want to take. So that this is just basically a concentration. It's a dimensionless number. And then you can, what is really important is that you can actually, instead of just the mean concentration, what is really important from the point of view of mixing is the standard deviation. So how well mixed is it? Well, the standard deviation will tell you, and let's call this S as the standard deviation. Then that is just equal to sigma I equal to 1 to n. So this is your standard deviation. So this is one typical way of measuring how well things are mixed. And you can, what you'd like is that at long times, of course, you expect that every sample will have a concentration that is equal to the mean value. So that is xi is equal to xi bar everywhere. That is perfect mixing. And then the standard deviation will be 0. So and you can even calculate what will be the standard deviation at the initial stage. Okay. And let's say we started with a completely segregated system. So this quantity concentration, this volume will be proportional to x bar, and this volume will be proportional to 1 minus x bar. So your standard deviation, will be we can calculate for complete segregation. That is when everything is either over here or over there. So either you're black or you're white. So if you are black, then xi is equal to 1. And then the probability of getting that is x. And then here, if you go here, then your concentration xi will be 0. And then the probability of getting that is 1 minus x bar. So, so if you see this, instead of writing as sigma n into this, I can write it as the probability of, let's call this as A to be in region A, and this is, let's say, region B. So this is probability of being in region A into the concentration at xa minus x bar whole squared plus probability of being in region B into the concentration at xb minus x bar square. So, we have replaced this whole summation and all by just writing it as probability. So, it's like the fraction of samples in A will be proportional to PA and the fraction of samples there. So, you have two sums, and since, the concentration is known over here, so this is XA in PA, X is just equal to 1, and the probability is X bar. So this is equal to X bar into 1 minus X bar whole square, plus the probability of being in region B is 1 minus X bar, and the concentration is 0. So you can see here, this is just equal to X bar into 1 minus X bar whole squared minus X bar squared into 1 minus X bar raised to the power of half. So now if we take this common, then what you will get is this is equal to X bar into 1 minus X bar, and then you multiply that by 1 minus X bar, I'm sorry, this is plus here, plus X bar raised to the power of half. So if I call this as S0, and let's call this as S infinity, then what you will get is, for complete segregation, your S0 is just going to be equal to X bar into 1 minus X bar raised to the power half. So in this way, we can actually define an intensity of, you can define now some sort of mixing measure, which could be something like S by S0, which is going to be now less than or equal to 1. So the highest value that this S can take is this, and then for complete segregation, and when it's perfectly mixed, it will go to 0. So you can start with, let's say, 1.0 for this measure. Let's call this as I, intensity of segregation or something like this. So it starts with 1 and then it goes to 0. Or it may go to 0 in a slow way also. So, depending on this, it may actually go something like this. Okay. So this is one thing. And in the next class, I'm going to tell you a little bit more because since we take finite samples, your S infinity is never quite 0. So there may be other. This particular measure is called the intensity of segregation. And in fact, what I'll try and show you also next time is that in some of the cases, it may actually go like this, that things may mix for a while and then they will start unmixing. And that is due to segregation, that is, the particles actually separate out. So we'll look at that also in the next class. Okay, so I've gone a bit over. Let me now stop here, and now let's go over to the quiz. We will start the